Yeah, welcome back. In this lecture, we will talk about two-stage compression with water intercooler and liquid subcooler. We have already done two-stage compression with the liquid intercooler in the class already. Okay. So now if you look at the layout, so you have the refrigerant entering the evaporator, and from the evaporator, it goes to the low pressure compressor. Okay. Once the refrigerant gets compressed in the low pressure compressor, it goes to the water intercooler. Okay. Just give me a second. Yeah. Okay. So once it goes or it comes out from the low pressure compressor, it enters into the water intercooler. So here the de-superheating takes place. And in the previous case, when we used the liquid intercooler, the de-superheating took place to such an extent that this state point number 3 was the dry saturated state. Okay, but when we use water intercooler, it is not possible for when you use the water intercooler, it is not possible to de-superheat it in such a way that it reaches the dry saturated state. There is still some amount of superheating that is left out in the refrigerant. Okay, so that superheated a minimum amount of superheated refrigerant that is compressed in the high pressure compressor. It is then taken to the condenser where the vapor gets converted into the liquid, and the refrigerant liquid is further subcooled in the liquid subcooler. Okay, and that is after liquid subcooler you have state point number 6, and from the liquid subcooler it enters into the expansion valve where it expands, where the pressure drops. Okay, and then it is taken back to the evaporator. Okay, now if you look at the pH diagram, here I have state point number 1, and my state point number 1 is on the dry saturated state, which is default, and in the low pressure compressor it is compressed to state point number 2. Okay, and then you have 2 3, which is the water intercooler. As I said already, it is not going to de-superheat till it reaches the dry saturated state. It is still in the superheated region. So this is your point number 3. Point number 3 is still in the superheated region, and then it enters a high pressure compressor, which is further compressed to point number 4, and then in the condenser it is condensed back to the refrigerant liquid at point number 5. But then we again use a liquid subcooler where it is subcooled further to point number 6, and then in the expansion valve it expands to point number 7, and then in 7.1 where your evaporator is, the heat extraction from the refrigerated space takes place over here. Okay, so this is your pH diagram, and the emphasis is where you use the water intercooler. So in the water intercooler, when you de-superheat it, it is not going to reach the saturated vapor state. So let me point it over here. When you use a liquid intercooler, it would have, the 2 3 would have been this blue color line, but now what we have is a red color line, which is 2 3. So the refrigerant is still in the superheated state. Okay, so that is the difference between water intercooler and liquid intercooler. So here we use a water intercooler where the liquid refrigerant is still in the superheated region of space. Okay, so now what we will do is we will look at a simple problem, a sample problem involving water intercooler and liquid subcooler, and let's see how to deal with such problems. Okay, the following data refers to a two-stage compression ammonia refrigeration system with water intercooler. Okay, so the system that we uses ammonia as the refrigerant. The condenser pressure is 14 bar, the evaporator pressure is 2 bar, intercooler pressure is 5 bar, and load on the evaporator is 2 ton of refrigeration. So when you say load on the evaporator, that is the heat extracted from the refrigerated space, which is 2 ton of refrigeration. 1 ton of refrigeration is 3.5 kilowatt. So 2 into 3.5 kilowatt, that is going to be 7 kilowatts. Okay, and further they have said if the temperature of the de-superheated vapor that is in the water intercooler, and the subcooled refrigerant, they are limited to 30 degrees centigrade. So after desuperheating as well as after subcooling, the refrigerant temperature is at 30 degrees centigrade. So they want us to find the power required to drive the system, and they also want us to find the COP of the system. And one point I forgot to tell you here. So let me go to the previous slide over here. So if you look at this particular schematic layout, see the mass flow rate is same everywhere. The mass flow rate is same in the low pressure compressor and as well as in the high pressure compressor. So when you use a liquid intercooler, you would have one more line over here, a vertical line over here. So let me draw that with a blue. So you will have a line over here, so which indicates that you will have M3 passing through the water liquid intercooler. M1 is the mass of the refrigerant that flows across the low pressure compressor, and M2 is the mass flow rate that flows across the high pressure compressor. Okay, but in this case where you use the water intercooler and liquid subcooler, you are going to have a common mass flow rate. So the only mass flow rate that you have is M. So when you say mass flow rate, it's going to be M dot. Okay, so you are just dealing with one mass over here. Okay, so it is the same mass of refrigerant that flows everywhere. So there will not be any confusion at all in while dealing or solving with this particular problem. Okay, so now if you draw the pH chart for that, just like we saw in the previous slide. So if you look at the pH diagram, so let me use another color for the processes. Okay, so I start with point number 1. So 1 to 2 is going to be my compression in the low pressure compressor. Then 2, 3 is my water intercooling. So point number 3 is not on the dry saturated vapor line, it is still on the superheated state. And 3, 4 is the compression in the high pressure compressor. And then I have 4, 5, which is condensation. So let me write 5 over here. So this is my 5. And then you also have a liquid subcooler. So it is subcooled to point number 6. And then in the expansion valve, you expand it to 7. So 7, 1. Sorry about that. So 7, 1. This is supposed to be a horizontal line. Okay, so 7, 1 is your heat extraction in the evaporator. Okay, so this is the pH chart that we have. So 1, 2, that is going to be isentropic compression. 2, 3 is your water intercooling. 3, 4 is isentropic compression again in the high pressure compressor. 4, 5 is the condensation process, and 5, 6 is subcooling, and 6, 7 is expansion in the expansion valve, and 7, 1 is heat extraction in the evaporator. Okay, so let me use a green color over here to indicate the pressure levels. So this pressure level is going to be the pressure level of the evaporator. So pressure level of the evaporator is 2 bar according to the problem statement. And then we have the pressure level of the intercooler. So let me say PI, and that happens to be 5 bar over here. And then I have the condenser pressure PC, which happens to be 14 bar. Okay, so these are the 3 pressure levels. Okay, so now let's use the pH chart of the ammonia refrigeration system. Okay, and before proceeding further, let me also point out one more thing. Let me use a brown color over here. Okay, see, one point which they have mentioned is the temperature of the desuperheated vapor and the temperature of the subcooled liquid refrigerant, they are limited to 30 degrees centigrade. See, if you look at the temperature line looks like this. and then once it reaches the superheated saturated liquid line, it drops like this. So it is a vertical line from here, then there is a horizontal line, and then it drops down. Okay, so this temperature line over here is 30 degrees centigrade. So you can see point number 6 lies on the 30 degree centigrade line, and point number 3 also lies on the 30 degree centigrade line. Okay, so now let's go to the pH chart and let's fix the points over there. Okay, so this is the pH chart for ammonia. So we have 3 operating pressures. So one pressure is 2 bar. So this is my evaporator pressure. The other pressure was intercooler pressure, which is PI. And what was the other value? 12 bar or 14 bar? The other value is 14 bar. 2, 5, and 14. So this could be 15. So 14 is somewhere below it. So let me say this is my 14 bar. Okay, 14 bar is my condenser pressure. Okay, so now the point number 1, state point number 1, it lies on the evaporator pressure level. Okay, and that is on the saturated vapor line. So this is supposed to be my point number 1 over here. Okay, so shall we use some other color over here, because there is already a red. Let me use, I'm not sure whether yellow will be visible. Let's try. So this is, no, this is not good. Okay, there is no other go. Let's try and use this brown over here. So this is my point number 1. Okay, and we know that 1, 2 is going to be an isentropic process, so you have to follow the constant entropy line. You can look at the constant entropy lines, which are shown in dark blue color over here. Is equal to 6, x equal to 6.25, 6.5, 6.75. So if you look at our point, that is lying between x equal to 6 and s equal to 5.75. Okay, so I have to draw an imaginary line over here. So I have to draw a line which is parallel to the entropy lines, the constant entropy lines. Okay, and how far should I draw that? My intermediate pressure level is at 5 bar. So if I follow this 5 bar line over here, that should intersect somewhere here. Okay, so that is my point number 2. So this is my 1, 2. Okay, and then according to the problem statement, so here I have my red color lines that are dropping down. Those are the 30 degree lines, 30 degree centigrade lines. Okay, so here I have my 30 degree centigrade line, which is coming over here. So I am supposed to draw so this is my point number 2, and from there I have to draw a horizontal line, and so this is going to be my point number 3. Okay, point number 3 is on the entropy line s equal to 5.75, and once again I have to travel along the constant entropy line till I reach s equal to 14 bar. Okay, s equal to 14 bar, let's say, is over here. Okay, so if I travel along this S equal to, sorry about that. So this is my constant entropy line, S equal to 5.75. Travel along that till you reach the 14 bar line. So that is going to be my point number 4. Okay, and then from here I'm going to draw a horizontal line till I reach the condenser pressure line over here. So that is my saturated liquid line. I have to draw a horizontal line till I reach, oh, it seems my point number 4 is over here. So let's correct that. So from here to here, this is my point number 4. And this is my point number 5. Okay. And then here you have the 30 degrees centigrade line. So let me show that in red over here. So this is my 30 degrees centigrade line, and it is supposed to be a vertical line from here. Okay. So when I extend it, the problem statement tells us that it is subcooled to 30 degrees centigrade. So this point on the saturated liquid line is phi, and when I extend to 30 degrees centigrade, that is going to be point number 6. Okay, so this is phi and this is 6. Okay, then from here drop a perpendicular till it reaches the 2 bar pressure line. So this is my point number 7. And then from here draw a horizontal till it reaches point number 1. Okay, so now we have fixed all the points 1, 2, 3, 4, 5, 6, and 7. So now what we have to do is write down or note down the values of H1, H2, H3, H4, H5, H6, and H7. Okay, and all these values are in kilojoule per kilogram. Okay, because of the limited space that is available here, I am giving the common unit as kilojoule per kilogram, but it is, as I always tell you, it's a good practice to write the units immediately after the value of H1 till H7. Okay, so how do you do that? So this is my point number 1. Drop a perpendicular from here. Okay, so that is going to give me the value of the enthalpy. Okay, so the value of enthalpy over here is 1400, and the value of enthalpy over here is 1500. So it is somewhere between 1400 and 500. Okay, so uh, let me show that with a dark blue line. So this guy is 1300. This guy is 1400. This guy is 1500. And now our point, that is over here, this is my point number 1. So when I drop a perpendicular, my point is over here, which is very closer to 1400. So maybe 1430. So let's say 1430. So that is my H1. So H2, if I drop a perpendicular over here, so that is 1500 and a little bit closer to 1600, I believe. So here you have the 1600 line. So if you drop a perpendicular from 2, so that is somewhere closer to 1600, maybe 1580, let's say. Okay, so point number 3, if you drop a perpendicular again, somewhere 1540 or 1530, let me say 1540, and H4, so that is midway between 1600 and 700. So let me say 1650, and H5, between 300 and 400. So let's say 350, and 6 is say 330, and H6 and H7 would be the same because 6, 7 is a isenthalpic process, isn't it? Where H6 is equal to H7. So all these units are in kilojoule per kilogram. Okay. The question is, they want us to find the COP of the system, and they also want us to find the work input to both the compressors. Okay. So the net work input would be WLPC plus WHPC. Okay. So let me make use of this space available over here. Let me use the red color. So if you want to find the refrigeration effect, that is going to happen in the process 7-1. So that is going to be H1 minus H7. So the value of H1 over here is 1430 minus 330. So that would be 14 minus 3 would be 11. So 1100 kilojoule per kilogram. So that is our refrigeration effect. If you look at W, the work input to the low pressure compressor, that is process 1-2. So it is supposed to be H2 minus H1. H2 is 1580 minus 1430. So that is 150 kilojoule per kilogram. Work input to high pressure compressor, that is going to be process 3-4. So that is H4 minus H3. H4 minus H3 is 1650 minus 1540, and that is 110 kilojoule per kilogram. Okay, so if you look at the total work input, the W net will be WLPC plus WHPC. Okay, so that is going to be 150 plus 110, which is 260. Okay, so now if you look at COP, I'm sorry that we don't have any space over here. So let me roll it a little bit down. Say COP is refrigeration effect divided by work input. So refrigeration effect is 1100 whole divided by 260. So how much is that? Let me evaluate. So 1100 divided by 260, that gives you 4.23. So that is the COP of this particular vapor compression system, where you have the two-stage compression with water intercooler and liquid subcooler. Okay, so that's it for in this particular video lecture. Thank you.